In this video, we'll introduce the Zeeman effect. We'll start by discussing the different regimes in which the Zeeman effect acts. Then we'll talk about the weak field Zeeman effect and then the strong field Zeeman effect. So what is the Zeeman effect? When an atom's in an external magnetic field, B external, it interacts with that magnetic field, which then splits the levels. That's called the Zeeman effect. The interaction Hamiltonian for the Zeeman effect, H prime sub z, is equal to minus the sum of the magnetic moment due to orbital angular momentum plus the magnetic moment due to the spin angular momentum dotted into the external magnetic field. Well, mu sub s, we know what that is. It's equal to minus E over m times the spin vector. And the angular momentum, orbital angular momentum magnetic moment is just minus E over 2m, there's this factor of 2, times the angular momentum vector. Well, this means that when we replace this, we can get that H prime z is equal to E over 2m times the quantity L vector plus 2s vector dotted into B external. So the nature of the Zeeman effect depends on the relative strengths of the external and the internal, that is the spin orbit magnetic fields. Right, the spin orbit field is due to L. So when B external is much smaller than B internal, then you're in the so-called weak Zeeman regime. When B external and B internal are approximately equal, you're in the intermediate field regime. And when B external is much stronger than B internal, you're in the strong field regime. Depending on which regime you're in, you have to use perturbation theory slightly differently. So we'll start with the weak field Zeeman effect. So this is when B external is much less than the internal fine structure fields, and therefore the fine structure dominates, and the good quantum numbers are those of the fine structure, which are n, the principal quantum number, the angular momentum L, the spin angular momentum s, and then the total angular momentum J and m sub j, which is the magnetic part of the total angular momentum. We're going to apply first order perturbation theory to get the solution to this. And in this case, the Zeeman Hamiltonian is the perturbation because its field is much smaller than the internal field. So the correction, the first order correction to the energy, E sub z1, is equal to this inner product. It's n L j m sub j, h prime z, n L j m sub j. So it's the diagonal elements. Well, if I substitute in what h prime z is, I get E over 2m, B external, dotted into the expectation value of L plus 2s. Well, we can rewrite L plus 2s with j, because j is equal to L plus s. So this just becomes J plus S, and you have in front your E over 2m times B external dotted into the expectation value of J plus S. Well, we can evaluate this by realizing that J is just a constant, and that L and S are indeterminate, so the time average of S can be calculated. So if you look at the diagram here, you see J is a constant, and it's a certain length. L and S precess around J because the vector sum of L plus S is J, but only the Z components of L and S are possible. Only the components along the J direction are possible to know. The other components are indeterminate because L and S are precessing. So we can write the average value of S vector is equal to S dot J, that is the projection of S onto J, divided by J squared times J. So because we have J and J here, we have to divide by S squared, and that'll give us the average value of S. That is, the part that's perpendicular to J averages out because it's indeterminate. The part that's along J stays constant. So we're basically calculating the average value of S as being the part that's along J. And we've written it as a vector because we have this scalar product here, and then we have multiplied times a vector, and then we normalize out the magnitude of j. L then is equal to j minus s, and we can write L squared is equal to j squared plus s squared minus 2j dot s. And therefore, s dot j, which is the term that we need up here to get the expectation value of s, is equal to 1/2 times j squared plus s squared minus L squared. So we use the same trick as we do to calculate L dot s for the spin orbit coupling. But now it's a little bit different. We're calculating s dot j. Well, when I write this all out in terms of the quantum numbers and expectation values, I get h bar squared over 2 times the quantity j plus 1 plus ss plus 1 minus l plus 1. So the expectation value of the Zeeman energy correction, which is given as the inner product of L plus 2s plus times some constants out here, which is equal to j plus s, can now be rewritten in terms of our interpretation of s, which is the average value. So j plus s then becomes j times 1 plus s dot j over j squared. And now we can rewrite s dot j in terms of the quantum expectation values, the quantum numbers. So it becomes 1 plus 1/2, I took the h bar squared out, j squared plus L squared plus s squared, because j squared has an h bar squared also to it. And when I write that all out, I get 1 plus jj plus 1 minus LL plus 1 plus SS plus 1 on the numerator, and the denominator you have 2 times j plus 1. And the h bar squareds cancel in both these cases. And this is multiplying times the expectation value of j. Well, this quantity up here in front, we can rewrite, and by convention, we write it as g sub j. And it's called the Landé G factor. And the Zeeman energy correction then becomes E sub z, first order correction, is E over 2m times B external times G sub j, which is the Landé G factor, times H bar M sub j, which is the expectation value of the vector j, dotted into B external, which if we choose it to be in the z direction, we get H bar M sub j out for this expectation value. The Bohr magneton is EH bar over 2m, it's constant. And you can extract the Bohr magneton from here, you have E over 2m and an H bar here. And so this becomes, this expectation value, or the value of the Bohr magneton is 5.788 times 10 to the minus 5 eV per Tesla. And the energy correction then becomes the Bohr magneton times the Landé G factor, which depends on these terms here. This is the Landé G factor here. B external over M sub j. The total energy, therefore, includes both the spin orbit and the Zeeman corrections, and the two j plus 1 states have unique energies, because independent of what M sub j is, you're going to get a different value for the energy, right? So the energy depends on M sub j, so you split the degeneracies of the 2j plus 1 levels with this Zeeman effect. On the other end, you have the strong field Zeeman effect. So B external now is much, much bigger than B internal. In this case, the Zeeman Hamiltonian dominates, and the spin-orbit coupling is now the perturbation. So the Zeeman Hamiltonian is E over 2m L plus 2s dot B external. And the spin-orbit Hamiltonian is E squared over 8 pi epsilon naught L dot s over m squared c squared L plus times L plus a half times L plus 1 n cubed a cubed. We evaluated this last time. Now, because the Zeeman Hamiltonian dominates, you have to be in a basis set that works for the Zeeman Hamiltonian, and that is the basis set where you have good quantum numbers being n, L, M sub L, S, and M sub S. And the reason is, if you take B external in the Z direction, you will have L sub Z and S sub Z here. And you have to evaluate that. The energies have to be diagonal in this Hamiltonian, and therefore these must be good quantum numbers. You need eigenfunctions of L sub Z and S sub Z. Now, if you put this B external in the Z direction, the Zeeman Hamiltonian then reduces to the following. H prime Z is equal to E over 2m, B external, L sub Z plus 2S sub Z. And now if we, ignoring the fine structure, because we have to use that as a perturbation, the energies are now the Bohr energies, which are minus 13.6 electron volts divided by n squared, times the energy of the Zeeman terms, which are easy to compute because it's L sub Z and S sub Z, and these are good quantum numbers, M sub L and M sub S. So we get that first term, minus 13.6 eV over n squared, plus a Bohr magneton times B external times M sub L plus 2 M sub S. So these energies have some degeneracies because you can find, of course, for given n, you can find several values of M sub L and M sub S which gives you the same energy. For example, if you have M sub L and M sub S equals 1/2, then this term here will be M sub L plus 1. If you also have M sub L plus 2 and M sub S equals to minus 1/2, this will be M sub L plus 2 minus 1, which is M sub L plus 1. They both result in a value M sub L plus 1, independent of the value of L. Right? Because L does not exist in this, because L is only part of the spin orbit Hamiltonian. So fortunately, these states, the ones with good quantum numbers N, L, M sub L, and M sub S, besides S as well, are good states for the fine structure Hamiltonian because the degeneracies can be resolved by the L squared and J sub Z operators, which both commute with F sub S. So L squared resolves states of different values of L. So if you have different values of L, but degenerate energies in the Zeeman effect, then you have L squared will resolve this. And JZ resolves whether M sub S is plus 1/2 or minus 1/2, because M sub L plus 2M sub S is equal to M sub J plus M sub S, because M sub L plus M sub S is just equal to M sub J. And therefore, you can distinguish whether the sign is positive or negative for M sub S. That is, when you apply J sub Z, you'll be able to tell whether this combination is due to a negative M sub S or a positive M sub S, because you also know L. And so we can use these also for the spin orbit Hamiltonian. So if we apply first order perturbation theory to the fine structure Hamiltonian, and these are using problems 714 and 726, you get E sub Fs, the fine structure energy correction, is equal to the inner product of HR prime, which is the relativistic correction, plus H sub SO prime, with inner product with NL, M sub L, M sub S on both sides. Now S dot L, which is the spin orbit term, can be broken up into three terms. S sub X, expectation value of S dot L is equal to the expectation value of S sub X times the expectation value of L sub X, plus the expectation value of S sub Y times the expectation of L sub Y, plus the expectation of S sub Z times the expectation value of L sub Z. Now these two are indeterminate, right? So they give you 0, they average out to 0, and you're left with inner product of S sub Z and L sub Z, which gives you H bar squared M sub L times M sub S. And so in perturbation, the spin orbit Hamiltonian becomes very simple. It has this term H bar squared M sub L sub S. When you put that all together, you get the energy correction for the fine structure, including the relativistic term, is 13.6 electron volts over n cubed times the fine structure constant squared times the quantity 3 over 4n minus LL plus 1 minus m sub L n sub s. So this is the spin orbit term. And this is from the relativistic term, divided by L times L plus a half times L plus 1. And this holds for L is greater than 0. L is equal to 0 gives you a little bit of a problem here. But it can be calculated another way.